Now before we wrap up this part of the chapter, let's understand one more useful skill. In this video, we're going to learn how to find the total possible number of relations between two sets. For example, here are two sets. Set A has elements 1 and 2 and set B has elements A and B. Our job is to find all possible relations. Okay, do you want to give this a shot? Okay, let's try together. Let's figure out any one possible relation. Let's list down these elements. We have 1 and 2, A and B. Let's try visualizing the relation. Let's say 1 is related to B and 2 is related to A. These two are our ordered pairs. Okay, this is a relation. Let's try one more. 1, 2, A and B. 1 is with B, 2 is with A, and let's say 1 is also with A. Let's add the number of arrows. Is this a relation? Yeah, that's also a relation. Remember the frog who lives on land and water? So this is also a relation. But what if we have less number of connections? Let's say 1 is connected to A and that's it. 2 is not connected to anything. Is this a relation? Well, yes, this is also a relation. And let's go extreme. Let's say this is what we have. We have these two elements 1 and 2 and these two elements A and B, and they're not talking to each other. Is this a relation? Think about it. Well, yes, this is also a relation. Believe me when I say this, this is also a relation. Yes, in most relations, sets talk to each other, but then there are times when good, happily related sets are also not talking to each other. And if you still don't believe me, here's the real logic. Remember that a relation is a subset of a Cartesian product. The Cartesian product of A and B will have a lot of subsets. One of them will also be the empty set. Because empty set is a subset of all other sets, we can say that this relation, which is the empty set, is also the subset of the Cartesian product of A and B, which means this is also a relation. So what do we know so far? We know that a relation is a subset of a Cartesian product. If we want to find all possible relations, we need to find all possible subsets. And subsets of what? Subsets of a Cartesian product. So first our job is to figure out the Cartesian product of A and B. Let's do that. A, B, let's find the Cartesian product. So A times B, that's going to be this. 1 is with A, 1 is with B, 2 with A, and then 2 with B. This is what we get. Let's try figuring out some subsets. So one relation could be when we have these three elements, these three ordered pairs. We could also have, let's say, these two, the orange and the green one. We could also have the orange and the yellow one, and so on. These are good examples, but we're looking for all possible relations. How do we get to that? Well, to find the number of possible relations, we need to find the number of possible subsets. We've figured out the Cartesian product. Now our job is to find all possible subsets. Let's do that in an interesting way. Let's list the elements down. We have 1A, 2A, 2B, and 1B. And let's ask them to join our awesome subset. So we're making an awesome subset. Do you want to join us? Let's ask this to 1A. Suppose 1A says yes, I want to join. That's good for us. Even if 1A says no, we still have a lot more elements. So if 1A says yes, we'll ask this to the next one. We'll ask 2A. If 2A says yes, we'll ask it to the next one. Even if the elements are saying no, they're creating unique paths. Every single path will give us a unique subset. After 2A, we're going to ask this to 2B. And after 2B, we're going to ask this to 1B. After we are done asking all four of them, let's count how many different paths do we have. So we have 2 times 2, 4 times 2, 8 times 2, 16. We have 16 unique paths, which means we have 16 unique relations. And that's what we want to figure out. How many possible relations can we have? We can have 16 possible relations. Here's a closer look. Let's look at one particular path. Let's say we have this one. If we backtrack, which elements are part of this relation? So 1A said yes, 2A said no, 2B said no, and 1B said yes. So this relation has 1A and 1B. That's it. This is a unique relation. No other path will have just 1A and 1B. What about, let's say, this last one? We saw this one a few minutes ago. This relation is the empty set. And on the far left, we have yes, 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 and yes. We have a relation where every single one of them says yes. This is also going to be a unique relation. So 16 unique paths and 16 unique relations. You've solved the problem, but did you figure out the pattern? While you're thinking about it, here's a good visual that I made for you. Here are these 16 unique paths creating 16 unique relations. You can take a screenshot. All right, let's move. We have set A, set B, and the Cartesian product of A and B. And for this arrangement, the number of relations were 16. Let's try generalizing this. Number of elements of A is 2, number of elements B is 2, number of elements of A times B is 2 times 2, that's 4. And number of relations, the total possible number of relations, that's 16. 16 is actually 4. Because every element in the cross product had a choice to say yes or no. And because we made that choice 4 times for 4 elements, the total number of relations becomes 2 to the power 4, that's 16. This is where the magic is happening. So let's generalize. If number of elements of A is P and number of elements of B is Q, the number of elements of A times B is going to be P times Q, that's PQ. And the number of possible relations, the total number of possible relations, that will be 2 to the power PQ. That's going to be our formula. Let's wrap this up by plugging this formula in a different problem. We have this set A with 2 elements, set B with 3. Find the total number of relations. N of A is 2, N of B is 3, N of A times B, that's going to be 2 times 3, that's 6. So total number of relations become 2 to the power 6, that's going to be 64. And that's it.